For this problem, we are looking at this circuit diagram, and we are also given these two values for our unknown vg1 and vg2, so now they are known. We need to find the steady state time domain expression for our v0t of our circuit. So to start this out, I'm going to start labeling everything we have. We know that our voltage is going down this way, our voltage will be going this way, but for this one it will be going this way. This is the direction of voltage drop. And now we are going to be looking at our impedances. First, for our inductor, we know that the conversion for this is that we have a Z of L equal to our J times the omega times our inductance. And we know that our omega can be found in these given, so it's 5,000 times our 0.4, but we need to convert this to henries, so we're multiplying it by 10 to the negative 3, and this is going to give us a Z of L of J times 2. Now we need to do the same thing for our capacitor, however the formula is slightly different. We have a Z of C equal to a negative J over our omega times C. Plugging this into a calculator, we'll have negative 1 divided by 5,000 divided by 50 divided by 10 to the negative 6th, and the negative 6 is from our microfarads that we need to convert into farads. So we're going to get that our Z of L is equal to negative J times 4. Now we can start writing a node voltage method for this. We will be looking at this node right here and write our formula. So we will have our V0 minus from our VG1, which will be this right here. We're going to convert it to polar form, so it's going to be 10 with an angle of 53.13 degrees, and we're just going to plug this over here and then divide both of these by our J2 because this is happening over the inductor. Now we are going to add to this our V0 divided by our 6 ohm resistor, and then we're going to have a plus. We will have our V0 minus, and then since our VG2 is going in the up direction, we will have another minus, and then our VG2. Our VG2 is given to us right here, and to write this out, we see that it's a sine. We need to convert to a cosine. We know that cosine is 90 degrees behind our sine, so we will have cosine with a negative 90 degrees plus our 0 degrees because we have 0 degrees of an angle in here. And this is going to give us 8 with an angle of negative 90 degrees. And we can plug this in as 8 with an angle of negative 90. And this is all happening over the 50 microfarad capacitor, which we found to be negative J over 4. And per the node voltage method, we will be setting all of this equal to 0. Now from here, I'm going to factor out our V0s and then move the constants to the right side. When I was writing this in here, for some reason, I wrote the correct angle, but I forgot the 10. So this should be 10 with an angle of 53.13. This is going to be our new equation. Now we can divide all of these and then move our constants under these. So it's going to be a denominator. That way we can get our V0 by itself. And then we are going to convert these to rectangular form because we need to divide it by our J2. And to convert to rectangular form, we know that we are going to use the number, parenthesis, cosine of our angle, plus J times the sine of our angle. This is going to be our new equation. Now we need to convert both of these back to the polar form so that we may divide them. And we know the conversion to polar form is that we have our Vmax equal to the square root of our real number squared plus our imaginary number squared with our angle tangent of negative 1 with our imaginary number divided by our real number. And this is going to be our new polar equation. We are going to take our numbers and divide them, and then take these numbers or these angles and subtract the denominator angle from our numerator angle. And this will give us a V0 is equal to 12 with an angle of 0. So when we plug this into our answer, we are going to get 12 with an angle of 0 degrees. That is how we would solve this problem. If you want more network analysis problems, there's a playlist with more problems like this in the description. And if you want notes that go over this entire coursework, they will also be in the description below the like button.